All right, everyone. So we have chapter 14 here, which is superposition and standing waves. All right. So in this chapter, we're going to be learning about what we call interference, wave interference, which is when waves can overlap. And that's something that only waves can do, because imagine two balls moving toward each other. They can never occupy same space same time, right? They're going to just hit each other and then bounce back. They cannot go through one another, and that's something that waves can do. All right, so that's why waves are very different from particles. So you can say, right, an ideal particle is of size, of size zero size, is of zero size. An ideal wave is of infinite length. Two or more waves can combine at one point in the same medium, which means that they can overlap. Um, and I'm going to show you, let's say, in a few simulations where basically two particles, can never, occupy same space, same time. So if you have two particles moving toward each other like this, right? So they're going to collide. So let's say this is particle 1, 2, 1, 2. So they're going to collide, and then one will bounce back to the left, two will bounce back to the right, but they can never go through one another and continue their, original path. So this is something that waves can actually do, um, and we're gonna see examples of that. And this is known as the superposition principle. So if two or more traveling waves are moving through a medium, they can actually overlap, and the resultant value of the wave function at any point is the algebraic sum of the values of the wave function of the individual waves. Okay, so waves that obey the superposition principle are known as linear waves. And in general, linear waves have amplitude much smaller than their wavelengths. All right, so that means what we're looking at, in terms of the waves, you can see, right? So for example, you have one string, and something like this. Here's a string. So somebody oscillates on the left side and somebody oscillates on the right side. So this is a wave created from the left side and it's moving to the right. And this is the wave created on the right side and moving to the left. So you have two pulses traveling in opposite direction. And one of the things we can do, we can write the wave function basically for each one of them, right? So each one has its own, let's say wave function. So you can say, for example, let's say y1 is the wave for, the wave function for particle one. And let's say you started it, you started the on the left side, and it has, for example, a sine kx minus omega t, right? So let's say you have this one. And then the other one is then a sine kx minus omega t plus phi, assuming that there's a little bit of, um, phase shift or between, let's say, between them. All right, so think like this. Now then these two waves, right, traveling, moving toward each other. And we can assume that the pulses have the same speed, but even they can have different shape, or they don't even have to have different shape. They can even have the same shape. And in this particular case, one thing we say that they are in the same direction in a way that both of them have positive amplitude. So maybe this amplitude is +1, this one +2, okay? And then we're gonna have those pulses overlap. And then the wave function is the sum of the individual wave functions, basically. That means when they overlap, they create a new wave. And this new wave is then what we call a superposition of those two waves. All right, so now in terms of then what we can see when the waves start to overlap, so let's say here's the region when they start overlapping, then you can see, right, there's basically a new wave is constructed, right? There's a new wave, and the wave has, let's say, this y new wave, right? I don't know, y prime if you want to call this, is then mathematically is equal to the sum of the two wave functions, y1 plus y2. And then when the crests meet, right, when those waves overlap, when they crest or troughs, whenever they meet, whenever they occupy the same space and same time, there is then a new wave generated. And then the amplitude of the new wave will be in a way dependent on, let's say, what type of amplitude the original waves have, right? So you can say, right, when crest meets crest, the resultant wave has a larger amplitude than the either of the original waves. And then basically the two waves separate, and you can see, right, this was the first one that was moving to the right originally, it continues moving to the right. Second one that was moving left originally continues moving to the left. That means it's like nothing happened. But during this portion when they overlap, you can say that they construct a new wave where whose magnitude or the amplitude is equal to the sum of the amplitude of each individual waves. All right, so that's kind of what we have. Two traveling waves can pass through each other without being destroyed or altered. That means the original wave is still there after, sort of like, let's say they go through one another. So this combination of separate waves is in the same region of space to produce a resultant wave is what we call interference. And this is very unique to waves. Only waves can interfere in a way that like they can overlap. As I mentioned, right, the particles, for example, they can't. All right, so here I'm going to try to show you a simulation that kind of demonstrates this. All right, so I have found this website. Basically, they do nice simulations of some of the things that we talk about. So think like this. So we have two waves here, and it allows us even to change some of the values. For example, right now I can see that the pulse 1 has a height of equals 2, which is amplitude plus 2. The pulse 2 has a height of plus 3. For example, let me make them, both of them same height. So let's say, plus 2 and plus 2. Okay. And then one thing I can do here is, I can even change their width and things like that, right? So, but, for example, let's just leave it like this. I'm going to make the speed is a little bit slower when they start overlapping. So think like this, I'm running and you can see, right? They are moving toward each other. And then they start overlapping. Let me kind of then slow down and see what happens. When they overlap, when crest of 1, meets the crest of 2, see, there you go, generate a new wave. And you can kind of look at in terms of orange and blue lines as well. So they're going to come back. So we can see that again. So again, see, then they're moving and then they start overlapping. And as they overlap at any point, right, when they start overlapping, they generate a new wave with the amplitude, which is the sum of their initial positions. So the maximum occurs when the crest of blue and crest of orange meet. You can see, right, as soon as they overlap, then you get maximum amplitude. And then they continue moving in their, let's say, separate ways. All right. So then what happens here is this. So basically, let me see if I can write on this one. So let's say I have y1, as I mentioned, right, is a sine of omega t, no, sorry, kx minus omega t. Okay. And then the second one, let's write it like this in terms of a sine of kx minus omega t plus phi. And the reason is because let's say we can assume that first one starts from, x equals 0, y equals 0, t equals time, and the other one is basically some phi constant, later. All right, so, and then we just adding them together. We're adding them together. And then here we are using, some of the trig, identities. So this is for the, when you have sine of A plus sine of B, right? So basically you're adding two waves together. So the solution for this one is then 2 cosine A minus B over 2, then sine A plus B over 2. So this is what we get. Now for us, A is kx minus omega t, which is, the argument of the first wave. B is the argument of the second wave, which is kx minus omega t plus phi. So that's why if I'm calculating this, becomes 2 cosine A minus B over 2. Remember, I had this amplitude A over there already, right? Both of them have that constant. So then A times 2 cosine, so kx minus omega t, A minus then kx minus omega t plus phi. Then this is divided by 2. And then times sine of then kx minus omega t plus kx minus omega t plus phi, and this is divided by 2. All right. So from here, what we will see basically is this, right? In the first one, so kx and kx going to cancel each other. Omega t and omega t going to cancel each other. The only thing surviving is phi. For the second, in the sine argument, but by the way, these are multiplied, right? So I didn't have room. So there's a kx plus another kx. So becomes, so let me write down. So sine of, so becomes 2kx, then minus omega t plus minus omega t. So minus 2 omega t, and then plus phi, and this whole thing divided by 2. So that's why, in a way, I can divide each portion by 2. So 2kx divided by 2 becomes kx. 2 omega t divided by 2, negative 2 omega t. Then phi over 2 just remains phi over 2. That means over here, I basically end up with this. It's then kx minus omega t plus phi over 2, because this was the only term without 2. So I have to divide that by 2. That means combine them together, thing like this. When I add those two together, I end up with this. It's 2a, then cosine phi over 2, right? And then sine of kx minus omega t, then plus phi over 2. There you go. And this is my equation, right? So this is then the equation for the resultant, right, of the two traveling sinusoidal waves. That means, each individual wave. So right now, if I pause, there you go. So this thing like this equation represents this wave. This equation represents this wave. But their sum basically represents the wave when they overlap. So when they overlap, there we go. So that's the wave that, in black, right? That's the equation for that wave after they overlap. All right, so now, one of the things we can see here is this. So, all right, so hopefully you guys were able to follow. Again, you can pause, you can go back and look at this, derivation again. But let me kind of clear everything I have on the screen, and let me do this. So see, I am doing this for the two waves that have positive amplitude, right? Again, so let's see what happens. When they overlap, they create a wave with, much greater amplitude. So this is, we're going to see, right? This is known as a constructive interference. So this is constructive interference because they construct a much greater wave. Now let's wait until they somewhere over here, and then let's pause. And what I'm going to do, I'm going to make the other wave as -2. That means now they're in opposite direction, their amplitudes. Let's see what happens when they overlap now. See, now when they overlap, look at this. So you have orange and blue, right, for the individual waves, and then the black is their superposition. So see, when they overlapping, the crest of one basically ends up being with the trough of the other one, and you see what happens? There was basically no wave generated. This is known, now they're moving on their, their opposite ways. So what we have here is, let's see again. See, the instant the crest and the trough basically overlap. See, look at this line. See, this basically no amplitude at all. This is known as a destructive interference. That means they destroy each other because in a way the amplitude, right, is basically, let's say +2 plus -2, you get 0, right? Because, they have 0 amplitude when you adding to algebraically adding to quantities that are same, but one is positive, one is negative. And that's what we get. All right, coming back to this. So we have two things, right? You have a constructive interference that occurs when the displacement caused by two pulses are in the same direction. That means with both positive amplitude. So the amplitude of the resultant pulse is greater than either individual poles. We saw that. And then there's also destructive interference, which occurs when the displacements caused by the two pulses are in opposite directions. So then the amplitude of the resultant pulse is less than either individual, pulses. All right. That means when two pulses traveling in opposite direction, the displacement are inverted with respect to each other. Okay, so that means, you can have something like this, which, again, we saw. All right, so when they overlap, the displacements partially cancel each other. In any case, so what we get here is this. So this is the equation, right? So 2a cosine phi over 2 sine kx minus omega t plus phi over 2. Okay, so this equation, by the way, it's phi or phi, doesn't really matter. So let's call it phi over 2. Now, in terms of then what we have is that the 2a cosine phi over 2, this quantity is technically the amplitude of the traveling wave. Okay, so again, right, the resultant wave function is sinusoidal. It has the same frequency and wavelength as the original waves, and its amplitude is 2a cosine phi over 2, or phi over 2. So the phase is this phi over 2. All right. One of the things we have here is, let's say, what is this phi over 2, and when are we going to get a constructive or destructive, or thing like that? We can actually get that in terms of looking at this this quantity phi over 2. So think like this. So when this quantity phi is 0, all right, so then this cosine phi over 2 is equals to 1, right? So when phi is 0, cosine phi over 2 is 1, which means then amplitude is just 2a, because remember, amplitude for the resultant wave is 2a cosine phi over 2. So when the cosine of phi over 2 is 1, then it's just 2 times a. That means the crest of a one wave coincides with the crest of another wave. So crest on a crest, or trough or a trough, crest on a crest, trough on a trough. Well, that means, the waves are then everywhere in phase. We call them, they are in phase, right? With crests and a crest and a trough and a trough, they're in phase. And the waves interfere constructively. That means if I'm making another, let's say, maybe different color, let's say, in black. Let's say in black. So then this is then the resultant wave. That means, algebraic sum of those. So let's say. All right, and they're going to be constructively, interference. But, and in a way you can think of let's say if I come back here, so see the idea is that you want phi over 2, right, to be 0, right? So that you can have this, which means that it will happen as long as phi over 2, or you can say that, let's say the cosine phi over 2 is equals to plus minus 1, and amplitude will be 2a, right? So it's 2a here, or negative 2a there, 2a here, negative 2a there. That means in a way you get constructive interference as long as this is true. And this will be true as long as, let's say, this phi here is, right, or phi here is 0, 2 pi, 4 pi, and that. That means, even multiples. Even multiple of pi. Okay. All right, so then when phi equals pi, then cosine of the phase angle over 2 equals 0, right? Cosine of phi equals 0 over 2 equals 0, which means then the amplitude, right, equals 0. Amplitude of the resultant is equals to 0. So, and in this case, it's at the brown line over there in our graph. Well, it means that you get a wave, resultant wave, with no amplitude. All right, so that means it's an even multiple of pi. Okay. So, all right, so this should be actually odd. Also any odd multiples of pi, because if it's even, then 2 pi over 2 gives you 2 pi, that's not equal to 0. So odd multiple of pi. All right, so that means, For example, when phi is pi, or 3 pi, or 5 pi, and things like that. So then you're gonna get cosine of phi over 2 equals 0, because cosine of pi over 2 equals 0, same as cosine of 3 pi over 2, same as cosine of 5 pi over 2, right? And so on and so forth. And you get basically 0. So the amplitude is 0, and then the crest of one wave then coincides with the trough of the another one, right? So that's why they are out of, out of sync. So they're not in sync, they're out of sync, they're not or out of your phase, you can say, and you get then destructive interference, or they interfere destructively. All right, so those are the things that we get in terms of the waves when they are, overlapping. Okay, so, and what if let's say phi is either 0 or pi or something like that? If other than 0 or even multiple of pi, then the amplitude of the resultant is between 0 and 2, 8. That means it's neither the maximum amplitude or the, let's say, 0 amplitude, right? It's somewhere, let's say, in between. Again, so you can say that constructive interference occurs when phi equals 0, amplitude of the resultant is 2a. Destructive interference occurs when phi equals n times pi, where n here is an even integer. Amplitude here is 0. All right, so again, this should be odd for the destructive. It is even for constructive. That means, is 0, let's say pi, 2 pi. Let's say going, let's say from pi, right? So, this is 0 when it's equals to pi, 2 pi, 3 pi. Again, because you have cosine, if you do 2 pi over 2, right? Because, it's phi over 2. So this just gives you cosine pi over 2. Sorry. 2 pi over 2 divided by 2 is just pi, and so on and so forth. All right, so here I made a mistake. So it's 4. So it's 2 pi, 4 pi, 6 pi, and so on and so forth. So that, if you do that, you're going to get basically constructive interference, right? Because again, if you do 4 pi over 2, you cancel this, it becomes 2 pi. Cosine of 2 pi is again 1. Okay. So, so the general interference occurs basically where phi is between 0 and greater than 0 or less than, n times pi. And amplitude is then goes between those two, right? That means, for destructively interference, you get 0 amplitude. For the constructive, you get 2 pi. But, obviously you can get somewhere in between as well, right? So like, let's say over here, see that the crest of one is not with the crest of the other one. So then the resultant is with respect to some, midpoint for each one. Eventually, right, when they overlap crest and crest, then you're gonna, the wave will increase. So, but that also depends on, for example, as a function of time. All right. So the next we're gonna talk about in terms of how we can calculate mathematically positions of the, let's say, constructive or destructive, interference. And for this one, then one of the things we can do here is kind of understand how we can, let's say, remember, so we're considering, let's say, two waves, right? They're, overlapping and things like that. So we have to look at what we call path difference. So two different paths, right? So for example, so let's say I have actually I can show you again in a nice simulation. All right, so for example, here I have two speakers. So think like this. Now I have a lot of air molecules in front of it. So let's say what happens when I start one of the speakers. All right, so see, this generates waves, which is basically, remember, longitudinal wave, right? Which is just basically air molecules being pushed and pulled. And you can see, right, the wave is moving like this. So what I can do here is, you see, if I graph it, I can see it's a sinusoidal, right? So, and the crests are, kind of like moving like that. So, but the idea here is this. So you have one wave and it generates, one source, and it kind of generates its wave like this. So let's say source 1. And maybe, let's say now I have source 2. See, if I have source 2, then it's going to generate its own wave. So for example, if I have just a source 2, so it's kind of like generates its own, and it's moving like that. But now what I'm going to do, I'm going to then have both so they can interfere. So now I have both and now interfering. And now what we have here, those are then regions of constructive and destructive interference. For example, now what I have here is this. So there's a region of destructive interference and this is a region of constructive interference. So constructive, destructive, destructive, constructive, and so on and so forth. Okay. And one of the things I have, for example, let's say if I'm talking about this point P and I want to see if this is constructive or destructive, I will have to look at the distance R1 that wave 1 has to travel, and then distance R2 that wave 2 has to travel. And you can see, right, that's a, let's say different distances that they have to travel. So that's basically known as a path difference. Okay. And when I calculate in a way, so let's say R2 minus R1, I want to see, let's say, if I'm going to get a constructive or destructive. And constructive occurs, it becomes n times lambda. That means the quantity that I calculate is going to be some multiple of lambda. If it's destructive, then I'm going to get R2 minus R1, some n2 over lambda. Okay, so that means I'm going to get sort of like a fraction. So that's kind of what I'm, what we're going to be able to see, for example, in the next few slides. All right. All right, so again, so these are then two equations, right? So this is for the constructive interference, as I said, it's delta R, which is R2 minus R1 equals n times lambda. That means, one thing you can say is this: if delta R, which is equals to n times lambda, see if I divide both sides by lambda, so that means if I calculate or measure the position from one source to point P, and then the second source to point P, find their difference and divide by wavelength. And if I get n, and n here is some kind of, I don't know, like let's say 0, 1, 2, 3, right? Then, let's say I'm going to get constructive interference. Okay, so I get constructive interference, as long as, n is 0, 1, 2, 3, 4, 5. But if I get delta R over lambda, so let's say if I get 2, that means it's a constructive interference. But if I get here, for example, I don't know, 1.5, that means this is now a destructive interference, okay? That means, what I can get here is some kind of destructive interference because of its, in terms of the value that we get. All right, so that means that's a destructive interference. Or let's say if I get 3.5, or if I get, I don't know, 2.5 and, 5.5 or something like that. That means for the constructive, right? So I'm getting pretty much, you can say like an integer, right? So that means that the ratio of delta R over lambda is equals to some integer, or you can say that this, path length, right, is equals to integer times some kind of a wavelength. Or if you're using absolute value, then you can say a whole number times wavelength. And here you're going to again then get something like, let's say, a fraction. Okay, so where n in a way is, let's say an odd number, right? So n is so like an odd number. So that's why it's, for example, if it's 1, then becomes 1 times lambda over 2, which is basically 0.5 times lambda. Or if n is equal, let's say 1, so then become, when n equals 2, so that you have, well, it cannot be 2 because it's odd number, sorry. So let's say 3, then it's 3 halves, so becomes 1.5. 5 halves becomes 2.5, and so on and so forth. So that means it's a destructive interference. All right, so we're gonna then work and solve some problems here and look at in terms of, for example, how we can apply some of the things that we just learned to solving some of the problems. And yeah, even though they look kind of different from what we've been using, but you can see, right, they can actually be even, written in this type of format. All right, so we have two pulses traveling on the same string as described by, two function, y1 equals 5 divided by 3x minus 4t squared plus 2, y2 equals -5, 3x plus 4t minus 6 squared, then plus 2. All right, so the question is that in which direction does each pulse travel? Then at what instant do the two cancel everywhere? And at what point do the two pulses always cancel? All right, so that means for B, we are looking at the instant of time, and for C, we're looking at the sort of like position. Okay. So in terms of then part A, where it's asking in terms of the direction, if you remember, right, so that was y1 equals, we talked about, right, f of x minus vt, which means that, if it's, x minus vt in the equation, that means there's a negative, right? That means they're moving to the right. So, and there's a negative over here. So it is moving in a positive x direction. y2, then f of x plus vt, which means, here we have plus over there. So it is moving in a negative x direction. So that's for part A. All right, so for part B, what we have is this, then y1 plus y2 equals basically 0, okay? So then what we're gonna do here is we're gonna, say, all right, so it's 5 over 3x minus 4t squared plus 2 equals then -5 over 3x plus 4t plus 6 squared plus 2. All right, oh, sorry. If I do this add, then equals to 0, then in a way what I can do, so then I can say that this is equals to the negative of that, so this becomes, a plus. All right, so then I can, pretty much cancel the fives, do a cross multiply, cancel the 2's, right? And what I can get then this, 3x minus 4t squared equals then 3x plus 4t minus 6 squared. Sorry, I wrote this wrong over here. It's a minus 6. Okay. Then solve for that. So 3x minus 4t equals plus minus 3x plus 4t minus 6, basically taking the square root of both sides. So then from here, what we can get is this. From the positive root, we're going to get 8t equals 6. So then t is equals to 0.75 seconds, right? And then from the negative root, that means this is basically what we calculate for the time. And then for this is then end up being part B, and for the part C, negative root, right? So then, t's cancel out because if you're doing positive, positive root, then basically the x's cancel out, right? So if it's positive, x's cancel out. So then you're solving for the t. And if you're doing the negative root, then t's cancel out. So then you get in terms of the x, which gives you 6x equals 6. Then x equals basically 1 meters. Okay, so those are then the answers for that. Okay, that means you can say that at t equals 0.75, they cancel everywhere. And at x equals 1, they, the waves always, cancel. All right, so here's another example. So 2 identical loudspeakers are placed on a wall 2 meters apart. A listener stands 3 meters from the wall directly in front of one of the speakers. A single oscillator is driving the speakers at a frequency of 300 hertz. What is the phase difference in radians between the two waves, the waves from the speakers when they reach the absorber? All right, so again, similar to that speaker that I showed you, right? Example. So you can think like this. So you have, here's speaker 1 and here's speaker 2, okay? And let's say here's the wall and they are separated by this distance of 2 meters. So I can say that D is 2 meters. And then say there's a listener that stands 3 meters from the wall directly in front of one of the speakers. All right, let's put them right here. So this is the listener, where then I can say then this is the distance from the speaker to that, right? And this is like, let's say R1, right? So 3 meters. Now, what it means here is then when the speakers, both of them start working, right? So start oscillating, there's going to be a wave going from here to there. There's going to be a wave going from here to there. And then what we need to do here is figure out, let's say, you know, what we will have. So let's say this being then R2. And then let's say, what is the, you know, phase difference, right? So we're going to try to calculate that. All right, so obviously then what we do here is we look at in terms of finding the R1 and R2, and then, you know, using all of the information that we're given, because we're also given that there's a frequency of 300 hertz, and it's a sound. Sound has a, you know, a velocity of 343 meters per second in air. That means, you know, I can combine those two to solve for the wavelength, for example, right? Is then V over the frequency. So I can get 1.14 meters, okay? All right, so then using the equation that we learned, so then is delta X, or sorry, delta R is equals to R2 minus R1, and it's equals to basically N times lambda. All right, so we don't know what that N is, right? So let's say, is it N or is it N over 2? Or, so basically we don't know what it is. And the easiest way to do is to find that N, right? So basically to find that N. So the easiest way will be delta R over lambda. So to see what we're getting, are we getting let's say an integer, or are we getting, or the whole number, right? If I do absolute value, right? Am I getting a whole number, or am I getting like a fraction or something like that? All right, so let's say get then delta R over lambda. Well, what is delta R? Delta R is R2 minus R1 and divide by the lambda. And what is R2? Well, we're not given R2, but what I have here is this, right? You can see, right, there's a triangle, right triangle, where D2 is basically the opposite. Sorry, D2, D is the 2 meters is the opposite. R1 is the adjacent. So R2 itself is just basically, you know, using this triangle, I can say it's square root of, you know, 2 meters square plus 3 meters square, right? And then minus R1, which itself is 3 meters. And then it's divided by 1.14 meters, which is basically then my wavelength. That means then this ratio, right, delta R over lambda is equals to 0.53, right, of waves. That means this is basically in terms of that, what, you know, in terms of like, let's say the N that I get. All right, so then to find the phase difference in radians, what we do is this. Delta phi is equals to 2 pi n. Well, we just calculated our n, right? So then this is equals to 2 pi times 0.530. And then we get 3.33 radians. And that's our final answer. So that's the phase difference between the waves from the speaker when they reach the absorber. That means that they are, you know, 3.33 radian, you know, shifted by from one another. All right, so the next we're going to talk about standing waves. So here we're going to assume that two waves with the same amplitude, frequency, and wavelength travel in opposite direction in a medium. So you can see, right, two speakers like this, right? So here, like source 1 and source 2. So we take same frequency, same wavelength, and even same amplitude, right, moving toward each other. So here's Y1 and here's Y2. They interfere according to the superposition principle. Okay. So then the resultant wave is 2a sine kx cosine omega t. All right, so why is that the case? Well, let's see what we have. What we have to do here is we have to basically add them together, right? We have to add them together in terms of say, okay, so what, you know, y1 plus y2 is equal to this y prime, which is the resultant, or let me like y resultant like this. And that means what we're doing here is this. So y resultant is equals to a sine kx minus omega t plus a sine kx plus omega t, right? Plus means that this is moving in a, sort of like in opposite direction compared to the first one. Okay. Now from here, we can see, right? It's same amplitude, same wavelength. Everything is the same except that the direction is different. So we are then going to be using this one of the other trig identities where the sine A plus minus B equals then A cosine B plus minus A, so cosine A sorry guys, I missed something over there. So it equals to sine of A cosine of B, then plus minus cosine of A, and then sine of B. All right, so we're going to use this identity. All right, so that's why if I then use this, right? So if I then use this, I'm going to get basically, if I add those two together, we'll get this resultant wave. Okay, so this expression reduces to that. Again, taking the, A to be, kx minus omega t, B being kx plus omega t, just adding them together, right? I'm sure you can do that algebra. So we end up with 2a sine kx cosine omega t. 2a is basically, we can just factor out a's, right? So we can factor out a's and just basically get that. All right, so then this is then the wave function for a standing wave. So we call it standing wave because one of the things that we have here is, see those, let's say if here's a speaker one, right? So let's say speaker one and let's say speaker two, they're kind of trapped in this, going kind of like back and forth, like between them. So this is, we call it standing waves. All we're gonna see if there's a string wave, so it's gonna go like this and overlap and kind of go like that. That was bad, right? So something like that. So this is also like what we call a standing wave. So there is no kx minus omega t term, and therefore it is not a traveling wave. So this is in the resultant, right? When we see in the resultant equation, there is no kx minus omega t term. Okay, so that's why it is not a traveling wave. That's a requirement for the traveling wave. All right, so in observing a standing wave, there is no sense of motion in the direction of the propagation of either of the original waves. Okay, so that means, one of the things we can get from this is basically we see the wave kind of propagating back and forth, but then we don't necessarily see sort of like, let's say what's going on, let's say in which direction it is moving. And then there's a nice simulation that I can also show you in terms of, for you guys to have some kind of idea in terms of what the standing wave visually looks like. All right, so here's a standing wave. As you can see, right, so basically you have the wave just going back and forth like this. Can you tell in which direction it is moving? Not really, right? So you can't really tell in which direction it is moving, but it is oscillating back and forth like this because technically what happens here is when the wave is moving, so let's say if I stop like this, so think like this, when the wave is moving, there you go. So let's say it is moving like this and it hits this point and it reflects back. So it reflects back such that it basically goes sort of like in opposite direction. Let me try again. Kind of something like that. All right, so then it's, you can see, right? That's why it oscillates, sort of like, let's say back and forth. My drawing is not good, but let's say that's kind of like, you can see, right? It oscillates back and forth with respect to those. So, and that's why we call them standing waves, because it seems like they're standing on its, in the same, same space, right? But same place, but it's actually, going back and forth, with some frequency. Okay. So now, all right, so that's why if we come back here, then what we have here is this. So there's a node that occurs at the point of zero amplitude. Okay, so what does it mean? That means if I go back here and I kind of do drawing, so think like this. So here's a wave like this, and here's the next, another one. Okay, sort of like something like this. See, then this point over here, seems like those points have no amplitude. Those are known as node. Those are nodes. Basically everything in red. And then we have a portion where it has a maximum amplitude, right? So those are then the maximum amplitudes. Those are known as antinodes. So antinode. And one thing we can see is, like, let's say it's 1, 2, 3, 4, 5, 6 nodes, and 1, 2, 3, 4, 5 antinodes. And antinodes always one less. That means you have one extra node than compared to the antinode. Okay. So then that's kind of what we have. So think like this. Then if I'm looking at kind of like a, graphing like this and drawing a line like that, maybe my line would have been better if I did like in terms of like this. So think like this. Where is my first node? Well, my first node is at exactly x equals 0, right? Taking this to be 0. So it's exactly at x equals 0. Okay. And then where is my next node? Well, you can see, right? So this is a shape of one wave. This is one wave. Well, next node is exactly half a wavelength, right? Half of that distance. So half a wavelength. What is then the next node? Well, it's exactly one wavelength of distance. How about the next one? Well, it's 1.5 wavelength, right? That means 3/2 wavelength, and so on and so forth. Okay. Then where do I start my first antinode? Well, I start here, which is, well, a quarter of a wave distance from my reference position, right? So it's wavelength over 4, because remember it's a quarter of a wavelength. And the next one is here, which is basically goes like this, right? It's a, not quite one wave. So it's 3/2 wavelength, or 3/4 wavelength, right? Because this is quarter, this is half, and then this is the three-quarter of the wave. And then the next one is right here, which is 1 wave and a quarter. So it becomes 5 wavelength over 4 and things like that. Okay. That means this here shows that the nodes occurs at x equals 0. Okay. So I guess, using this color at x equals 0, and then half a wavelength and the wavelength and 3 of the half of a wavelength. So basically n lambda over 2 wavelengths. So n equals 0, 1, 2, 3. And antinodes happens at x equals, let's say, being consistent with the colors. So like, let's say, quarter of a wavelength, or 3/4 of a wavelength, or 5/4 of a wavelength, and so on and so forth. So basically n times lambda over 4, when n is a, odd number. You can see right here, n is basically a whole number, right? N equals plus 1, 0, 1, 2, 3, 4, and things like that. Where here n is an odd number. So 1, 3, and 5, and things like that. So that's basically where the antinodes occur. All right, so then what we get basically something like, again, so this is kind of like a better picture, right? So you can see that, what we get here is, a wave that kind of trapped and going back and forth like this. And when it does really fast, you basically see the segments, the shapes like that. And, it just basically kind of like stays like that. So again, this is a node. So here's a node, here's a node, and here's a node, right? So, and you can see, right, going from one node to another node, going basically this distance is half a wavelength. So going from one node to another node is half a wavelength. Going from one antinode to another one antinode is also half a wavelength distance. Okay, that means for every 2 adjacent antinodes or every 2 adjacent nodes, the distance here is, half a wavelength. But if you go from one node to another antinode, this is a quarter of a wavelength distance, right? Or from here, one node to another antinode, this is a quarter of a wavelength distance. All right, and amplitude is 2a sine kx. That means this equation that we derived, this guy here is the amplitude of the standing waves, okay? So again, amplitude of the standing wave, I usually write it like that. So is then 2a sine times kx, where again, k is the wave number. So it's 2 pi over the wavelength. All right, so then we can see that the standing wave patterns produced at various times by two waves are of equal amplitude traveling in opposite direction. So you basically get this. When you have two crests or two troughs, you basically get constructive interference. When you get crest and a trough or a crest, you get destructive interference. So this happens at t equals 0. This is t equals, a quarter of a period. And then half of the period is again, crest and crest, trough and trough, right? Because they're moving. So then you have, or, relative to one another, right? Let's say each trough, but, one is moving to the right, the other one is moving to the left, and kind of like back and forth like that. So a quarter of the period like that. All right, so that's kind of like, let's say in terms of sort of like the visual, understanding of that. And one thing we can do here is then we just use what we just learned, right, to solve a problem with a standing wave. So let's say you have two sinusoidal waves traveling in opposite directions, interfere to produce a standing waves with a wave function of y equals 1.5 sine 0.4x cosine 200t, where x and y are in meters and t is in seconds. And our goal will be to just determine the wavelength, frequency, and the speed of the interfering wave. All right, so, what you have to do is just write down the original equation where it's a 2a sine kx, right? And then cosine omega t. That means from here, you can kind of like look at it and compare. Okay, that means 2a is coefficient in front of the sine. That means 2a is equals to 1.5. In a way, then the amplitude is 0.75 meters, right? So you can look at it from that and just basically get just that information. All right, so then next is, let's say, what is the a wavelength? Well, where is wavelength? Well, you get wavelength from the wave number, that guy over there. Where that guy here is 0.4. That means I can say, all right, so for part A, k is equals to 2 pi over lambda, or lambda is equals to 2 pi over k. So it's 2 pi over 0.4. And if I do that, I'm going to get 15.7 meters. So that's my wavelength. Part B, the frequency. Well, the frequency here is I have an angular frequency over here, but it's asking for the linear frequency. Otherwise, it will ask for the angular frequency. When it's just frequency, it's a linear frequency. But we know that 2 pi omega equals 2 pi over f, which means f is equals to 2 pi over omega. And I can see, right, my omega, you can write it down, right? So then omega is equals to 200 radians per second. Let's say wave number was 0.4 radians per meters. So then here I can say it's okay, it's 2 pi over 200. And then this is going to give me 31.8 hertz. All right, so I made a typo, sorry about that. It's omega over 2 pi. No. Simple mistake. Let me see. So omega over 2 pi. So then 200 over 2 pi. So this is going to be then 31.8 hertz. That's my frequency. All right. Part C, it says, what is the speed of the interfering wave? Now I can do it in a number of ways, right? I can say, all right, speed is equals to wavelength times frequency, or it's equals to wave number over the angular frequency over the wave number. So any of those basically can work, right? So, and you just basically do whatever, let's say, whichever you want. For example, probably the easiest one is the second one, which is omega over k. So it's 200 over 0.4. I think it's just the easiest one. So we get 500 meters per second. Okay, so 500 meters per second. Okay, that's basically the speed of this, standing wave.